Hi guys, welcome to a lesson of ordinary differential equations. So in the previous classes, we discussed about some first order differential equations, separable equations, homogeneous equations, exact equations, and the equations reducible to exact equations. So in this class, we are going to start discussion on the linear first order differential equations, and we will see the general form, and we will see how to evaluate these first order linear differential equations by using some standard formulas, right? So the standard form of this equation is y prime plus p of x y equals to q of x. So where these p of x and q of x are simply functions of x, uh, and then we have y here with p of x that is linear. By linear, we means that the power of y is 1, right? So the power of the dependent variable should not exceed by 1 in the case of linear equations, and there should not be a term like this, y times y prime or y squared or y cubed like this, right? So to formulate these first order linear differential equations, we need the form of this type, right? So you have to check whenever you are solving a linear differential equation, whether it passes this test or not. So this is the litmus test of first order linear differential equations that should be compatible with this standard form, right? And then we have a simple formulation, that is we have to make this left hand side a complete derivative like this. For instance, we have d over dx into y e to the power x like this. So this is a complete derivative, right? So we have to make the left hand side of this form, then we can simply integrate both functions, both sides, to get the answer, right? And for this we have integrating factor that we also call it IF, that is integrating factor. And the method says that if we multiply this integrating factor with the whole equation, then we will get the left hand side like this. That will be a complete derivative. That will be d over dx times y mu of x. So we have an equation, linear equation of this kind, that is y prime plus p of x times y equals q of x. Then we have to simply find out the integrating factor by this formula. And for that, we need p of x, and we can easily get p of x from the equation, and we can find this by simply integrating uh, on the exponent, and then we can just simply multiply this mu of x to whole equation, that is mu of x times y prime, then mu of x times p of x times y, and mu of x times q of x. Then the solution to this equation can be easily formulated. We can just write this d over dx times y mu of x. It will be a complete derivative, so we can shift this d of x to the right hand side here, and then we can simply integrate both sides to get the general solution of this linear first order differential equation, right? So in fact, particular solution. So this is the formula for the solution. If we are able to find the integrating factor, then it's easily computable. So let's take an example here. And this is y prime plus 3y equals negative 9x. We will simply compare this given equation with the standard form, and we'll take out this p of x, q of x, and whatever we need, right? So we can see here that p of x times y, this term is equals to negative 3y, this term here. So we can compare and we can get p of x. So p of x is equals to negative 3. And for q of x, we have negative 9x here. So q of x equals negative 9x, right? Then we can just simply calculate the integrating factor, that is mu of x. So it will be e to the power integral p of x dx, where p of x equals to negative 3. So integral of negative 3 is negative 3x. Therefore, the integrating factor is exponential to the power -3x, and we can just simply multiply this integrating factor with the whole equation, and then we will get complete derivative on the left hand side. And again, we have the formula here, this formula, right? So y equals 1 over e to the power -3x times the integral of this function. And we know that the integral of this function, we can use integration by parts. We can take out this -9 from here to outside the integral because it's a constant, and then we can apply the integration by part rule here. So it will be x times e to the power -3x over -3 minus e to the power -3x over 9 plus c, that is the constant of integration, right? And then we can just simply multiply this term with all these three terms, and then we will get 3x, because this 3 here, -3 and -9. So -9 divided by -3 is +3, and e to the power -3x cancels with this e to the power -3x here. Therefore, we get 3x, and here we have -e to the power 3x over 9. Here we have -9 over e to the power 3x. So reciprocals, and they will cancel each other, and we will get 1 here. And then for c, -9 times c is c again, because c is an arbitrary constant. So anything is multiplied by this constant, it will be a constant anyway. So we can write it c divided by e to the power -3x simply, because e to the power 3x is a function, so we have to write it here, right? So we'll get the final solution of this form, where y equals 3x plus 1 equal plus c e to the power 3x. Then we have one more example, that is cosine x times y prime plus sine x times y equals 1. So first of all, this equation is not in the standard form. So to make this equation in the standard form, we will divide this whole equation by this cosine x. So we can divide the equation by cosine x like this here. So divide the equation by cosine x, and we'll just get the general standard form like this, right? So we have y prime plus sine over cos is tangent x times y, and 1 over cos is secant x. Then we have p of x here. This is p of x. And for integrating factor, we have mu of x equals to the formula e to the power integral p of x dx. So the integral of tangent x is ln secant x. So this e to the power ln secant x means secant x, because e will cancel with ln, right? So anything, any power raised on the exponential with ln is just simply the function inside the ln, that is secant x in this case. So the integrating factor is mu of x equals secant x, and then we have the formula to find this particular solution. So y equals 1 over mu x times integral mu x times qx dx. So it's 1 over secant x times the integral of secant x times secant x, because mu of x is secant x, and again q of x is also equals to secant x, right? So it's secant square x, and we know that the derivative of the tangent x is secant square x here. So we can just simply plug in the value, that is the integral of secant square x will be the tangent x, because this is antiderivative the integral. So we have y equals 1 over secant x times tangent x plus c. Then we have the solution by simplifying this equation. So 1 over secant x is cosine x, and tangent x plus c times cosine x. So in this way, we can solve first order linear differential equations, simple equations, simple solutions, standard forms. And first of all, the main idea that you should remember for these types of equation is the standard form of the linear differential equation, and then the integrating factor, and then the standard form of the solution. So that's all for the time being. Thanks for watching the lesson. And in the next lesson, we'll come up with the Bernoulli's equation. Thanks for watching the lesson. Goodbye.